Chapter 5, Systems and Matrices. This is the list of items I have for you. These are the topics that we will be addressing in this chapter. I will have a video lecture for each section, of course. So this lecture will take on systems of linear equations. And then we go sequentially, and notice that section 5.4 is missing from the list. That was intentional. Section 5.4 talks about partial fraction decomposition. And that one, chances are if you go as far as you need to, the instructor at that point will have to review partial fraction decomposition anyhow. So we can actually omit it because it's optional for our curriculum. So let's go to section 5.1. In section 5.1, we're looking at systems of equations. More specifically, we're looking at systems of linear equations. Now, a system, what is a system for us? Anytime we have two or more equations and we're interested in finding the common solution, then we have a system. So for example, let's say my system could be something simple: x plus y equals 5, 2x minus 3y equals 7. That would be a system because there are two equations in it. There's really no limitation to number of equations depending on the complexity of the system. It could be two equations, 3 unknowns, two equations, 5 unknowns, 5 equations, 5 unknowns. So however many finite number of equations, and depending on, again, the situation, we could have as many variables for each equation. So what I have here is a system of linear equations where I have two equations and two unknowns in this case. Our linear systems, the ones that we take on in this chapter, are typically in the form of a1x1 plus a2x2 and so on, plus a sub n x sub n. So in other words, equal to a constant. The x's here are the variables, by the way. So for example, I could go 2x1 plus 3x sub 2 minus 4x sub 5. Notice I skipped x sub 3 and 4. I have x sub 5 plus x sub 7 equal 10. So that would be an example of an equation. We call these first degree linear equations. First degree because the degree on the variable is 1 simply. Okay, or what I have here would qualify as a first degree linear system because the degree on x and y is each 1. Now, how are we going to solve the systems? And our focus, by the way, our focus in this section is two equations, two unknowns, and then we'll see an example of 3 equations and 3 unknowns. So when we solve the system, by the way, we have different methods of solving it. For 2 equations, 2 unknowns, we can do it using graphical method, which I will skip. And then we can do this using substitution method. And we can do it using elimination method. We look at other methods as we go on to future sections. So those are the 3 popular methods. You probably are familiar with these already from your algebra classes. So what happens when we graph 2 equations? What you're looking at is the number of possibilities that could happen anytime we graph 2 lines. Because these are linear systems, by the way, the graph of each equation, if we graph them, the graph would be a straight line. Now, a number of 3, to be specific, of possibilities could happen when we graph 2 lines. It could be a situation where the 2 lines cross at a common point. I'm looking at the first one on the left. So for this one, again, you have a common point of intersection of 2 lines. That common point is where the solution is. So right in here, that is the solution to the system. That system is called consistent system, and it has 2 independent equations. Okay. The middle one is an example of an inconsistent system. Inconsistent systems are systems that do not have a solution. because there's no point of intersection or intersections. This would be an example of an inconsistent system. Independent equations, of course, means there's no correlation between the equations. There is no connection, each its own. And this middle system is the one that has no solution. The first one had a solution. All right, and then we go to the last possibility. The other thing that could happen is when we graph any two lines, one line could overlay on top of the other one. So actually there are two lines here that we don't see. There you go, that's the second line overlaid on top of the first one. So if this is the first line, this would be the second line. Remember, because we have two equations, two unknowns. And there you have it. So with this system, there are infinite number of solutions. The system is consistent, and the equations are dependent equations in this case. So we often call this a dependent system. So keep in mind that there are infinite solutions in this one versus one solution. Now, ideally, we would like to have a system that has a unique solution. So our first case would be our best case in this, in these possibilities. And we will look at an example where we have a dependent system and how we can actually write the solution set. Now, before we actually proceed to solving systems, we're going to look at a set of what we call elementary row operations. That's what these are. We call these, or elementary operations, which we can do on the system. Now, there are three of them. The first one says that we can swap out, we can exchange, we can interchange any two equations in the system. Okay, the result would be an equivalent system. So an example of this, for instance, let's say I have x plus y equals 7, x minus y equals 5. If I use item 1, swapping out equations, of course, should not have any effect on the solution to the system, correct? And there you go. It's the same system. Doesn't matter whether I write the first equation first, second, or if I write the second equation first equation second. So that's what that says. Sometimes we use this property in order to maybe put a row that has maybe a coefficient of 1 on top, and then use it for subsequent operations, number 2 and 3. Okay, and then we have number 2 here. Number 2 is simply the multiplication property of equations. That says you can multiply or divide any equation. Notice that is what the multiplication equation is, the property of equation is. You can multiply, divide any equation of the system by a non-zero real number. Non-zero, because what happens when we multiply by 0? Everything disappears, right? So we don't want to do that. Therefore, for example, let's say I have an equation that is 1/2 x plus 1/4 y equal 3/8. So this number 2 here, the number 2 elementary operations, is going to help us a lot here. If I multiply both sides, not one side, both sides by 8, distribute, I get 4x plus 2y equal 3. Notice how much nicer that equation looks. So that's the use of property number 2. Number 3 is interesting, a little wordy, but number 3 allows us to replace. That's the only property that allows us to replace an equation by something else, if that's what we want to do. So that something else should be the sum of that equation and multiple. That equation would be the row you want to replace. Say you want to replace any equation. I keep saying row because I'm thinking matrix ahead of time, sorry. Equations. So I can replace an equation by sum of that equation would be this one, the one that we want to replace. The sum of that equation and a constant multiple of another equation in the system. Okay, I'll show you these. It's best done using examples, which we'll look at in a moment. Okay, so let's actually look at an example here. All right, our first example. So let me move this up. All right, so let me make something up here. In this example, suppose my system, have a curly brace on the left. That just means this is a system. That's all. The book doesn't do it. You could leave it out. You could do it. Doesn't matter. And suppose I have 3y minus x is equal to 10. All right, so let's try to solve this. Again, I don't want to graph it, but let's use substitution method to do this. Okay, so I'm using substitution method. Now, in substitution method, you have to choose an equation and a variable in that equation. So usually we choose variables to solve for because we need to substitute for those variables in another equation. So we typically pick variables. If we have the option, we pick variables that have coefficients typically 1 or -1 to solve for. We could solve for variables that have none other than 1 coefficient in front of them, but that will introduce fractions into the system, and I'm sure I haven't met a student yet that likes fractions. So I'm sure chances are you don't like fractions. Personally, I don't care for them either. So let's solve for, again, you have a choice of x or y, and it really doesn't matter, especially for this example. So I'm going to solve for y in that first equation. So my first equation is 7x negative y equals -10. All right, now to solve for y, I'm going to move y to the right side, bring 10 to the left side, so I get 10 plus 7x, or 7x plus 10, doesn't matter. And there. So you solve for the variable of your choice in the equation of your choice. And then I'm going to substitute, hence the name substitution. We're going to substitute in the other equation, the second one. If you plug it back into the first equation, this one, you simply get an identity. The equation is going to say -10 equals -10. So it doesn't help us solve anything. So let's substitute for y in the other equation. So this other equation now is 3y, but then remember y is 10 plus 7x minus x equal 10. Notice we reduce it down to one equation and one unknown. So we should be able to solve this equation now. Distributive property, 30 plus 21x minus x equals 10. Combine like terms, 21x take away x makes 20x. And at the same time, let's subtract 30 from both sides. So that's 10 minus 30. Subtract 30 on this side, of course, those disappear. And I have 20x equals -20 divided by 20, x becomes -1, and there is a solution to x by substitution method. Now, of course, we solve for one of the variables. We need to solve for both variables, correct? At this point, we're going to back substitute in here for x and determine what y is. So back substituting, I'm going to get the following. I'm going to have 7 times x plus 10. I'm looking at this equation, folks. It's 10 plus 7x. I did 7x plus 10. Addition is commutative, so that is okay. So from this, y ends up being 3, right? 10 minus 7. And there we have a solution to the system. The solution is in the form of an ordered pair. So the solution set has one ordered pair in it. -1, 3. And there you have it. We are done. So if I was to, let's say, solve this equation by graphing method, you would expect two crossing lines, line 1, line 2, and the point of intersection would be precisely -1, 3. That's the significance of this. -1, 3. Again, my lines are generic lines. I just drew them crossing like that. So there you have it. An example of system that is consistent and it has one solution. The requirement for consistency, by the way, is to have at least one solution. That's why dependent systems, the ones with infinite solutions, are also consistent. All right. Let's take a look at another one. This one, I'm going to have some fractions in it, just so we are not afraid of fractions when we see them. I know they may be intimidating, but we'll deal with them, no problem. So let's take a look at this one. I have x plus 2 divided by 4 and 3y plus 2 divided by, let's go 5, equal negative 3. All right. Now, this, we also want to solve this by a substitution method. Notice again the fractions don't look good. So I'm going to use property number 2 of systems. Okay, the elementary operations. Multiply, divide equation by non-zero real number. Okay, so I'm going to multiply the first equation, the first one, by, let's multiply it by the LCD. That's what we typically multiply by. And each equation, remember, these are independent equations, so you don't have to multiply by the same thing. So in the first equation, I'm going to multiply by 10. That's the least common denominator of 5 and 10, or the least common multiple, whichever you call it. The second equation, I'm going to multiply by the LCD of 4 and 5, would be 20, right? Least means the smallest multiple of those is 20. The other multiples would work, but we want the smallest. We don't want, for example, multiply the equation by 100. That just makes the numbers too big. So let's do now what we decided to do here. I'm going to multiply the first equation by 10. When we divide 10 by the first fraction, 10 divided by 5 is 2. So I get 2 times x plus 6 and plus, I'm doing distributive property. When you do 10 times fraction divided by 10, see the 10s cross out. So I only have 2y minus x. And so that was distribution to the second fraction. And remember, 10 reaches all the way to the other side of equal sign, multiplies by 1 also. And let's do the bottom one. The bottom, 20 times the fraction. You divide 20 by 4, we get 5. So that's going to be 5 times x plus 2. And then you divide, distribute 20 to the second fraction. And this time, 20 divided by 5 is 4. So I get plus 4 times 3y plus 2 equals. That one is done. And 20 reaches all the way to the other side. 20 times 3 is 60. Negative. Good. Notice the fractions disappear in one step. So don't let the fractions bother you. We can deal with them. Next step, we're going to distribute. Distribute 2 times x plus 6. So we get 2x plus 12 plus 2y minus x equals 10. The bottom, I get 5x plus 10 plus 12y plus 8 equals negative 60. First equation, combine like terms. 2x minus x would be x plus 2y equals. Move 12 to the other side or subtract it from both sides. And there, that's what that is. And then the bottom one, we have 5x plus 12y. So that's 5x plus 12y equals 10 and 18 here make, or I'm sorry, 10 and 8 make 18. True. And subtract 18 from both sides, we get negative 78. All right, so I did 10 and 8, 18. Subtracted it from both sides. Now, there we have it. We have a system that's reduced. This is all just so we got rid of the fraction and transformed it into a different system. So for this one now, if I solve by substitution, I can see that in the first equation, x is the easiest variable, easier of the two, in the better of the two equations to solve for. So I'm going to isolate x in the first equation. That would be negative 2 minus 2y. And then we're going to substitute for x in the second equation. So that's going to be 5 times x plus 12y equals negative 78. Distribute, we get negative 10. Negative 10y plus 12y equals negative 78. All right, and combine like terms, that makes 2y. Add 10 to both sides, we get negative 68. Okay, and then divide both sides by 2. So this becomes negative 34. And this one is taking longer because we had to do all the upfront work to turn it into a friendly system that this is. Now, once we solve for y, we can back substitute in the first equation and solve for x. Therefore, x is going to be negative 2, negative twice y. And that's going to be negative 2. Negative times negative is positive 68. 68 take away 2 would be 66. And we have the solution to x. Therefore, the ordered pair, the solution to this system, is going to be 66 comma negative 34. Kind of unusual answer for us. Usually our answers are single digits, but that's okay. Again, anything could happen. Sometimes we end up with irrational numbers, decimals, what have you. And there you go. So we have another example of a consistent system that has a unique solution. And that's what we like, by the way. We like to have unique solutions. It means there's just one of them. All right. So this is the gist of substitution method. Now let's solve, let's say, another same system. In fact, let's do, how about this one? 7x minus y equals 10. 3y minus x equals 10. The first one was negative 10. Okay, I'm going to use this time the elimination method. An alternative to substitution is elimination method for solving systems. Now with elimination method, so let me write the system again. It was 7x minus y equals, I believe it was negative 10. And then 3y minus x was equal to 10. Now first thing I want to make sure, when we do elimination method, we like to have all the variables on one side, left side that is, and the number, if any, on the right side. The variables must line up appropriately. Notice how they're crisscross right now, x and y. So it doesn't matter. Usually we go alphabetic order. So I'm going to keep the first equation. Second equation, I'm going to switch the position for x and y. And now we have it in what we call a standard form. Okay, at this point, we need to choose to eliminate one of the variables. And again, we choose the better of the two variables, x or y, to eliminate. Here, what's a better choice? A better choice would be one that has a coefficient of 1 or negative 1. Now, what if we don't have that? Well, we'll look at that. In fact, let me see. Yeah, this one has a 2, but I'll do an example where we don't have 1 or negative 1 in front of the variables. How do we work that? But for this one, it doesn't matter. Again, let's get rid of y. Get rid of y. Now, in order to get rid of y, our focus is just on y, by the way. Do not look at the constant. Do not look at the x's. Okay. So, there. Let me just put line through them. I'll remove those in a moment. The beauty of working with digital pen is this, that you can just make a mess and then just magically remove it. It looks as if nothing bad happened. Okay, so again, I'm just emphasizing the focus is just on the variable you want to eliminate. So y here. Now I have 3y in the bottom, negative y on top. In order for 3y to add to 0, it needs to be combined with its opposite, right? Negative 3y, because we know opposites add to 0. We want to eliminate. Eliminate means 0 on the variable side. So the question is, well, how do I create opposite of 3y, which is negative 3y? Here's the magic of digital pen. There you go. Now, how do I create a negative 3y? Well, to create it, we can multiply the first equation by 3, couldn't we? Remember, we can, that was property number 2 of systems of equations. We can multiply an equation by a non-zero constant, and I did. So when I do multiply, let's see what happens. So we get 21x, negative 3y. That's the opposite that we were seeking. And no surprise, because that was intentional, right? Intended consequence. And there you have it. Our intended consequence is this. We want those to be opposite, and we forced them. We created the opposites. So 21x minus x, that would be 20x. And on the other side, we have negative 20. Divide by 20, and we get negative 1. Nice and clean. And you wouldn't expect the solution to change, correct? You would expect to get the exact same answer for x down here as we did up here. And of course they do. They end up being the same. And now that we solved for one of the variables, the other variable we can solve by, again, substitution. You can back substitute for x in either of those two equations. So I'm going to substitute for x in the second equation because its coefficient is easier to work with. So I'm looking at second equation now. That reads 3y minus x equals 10. Plug in an x, which is negative 1, the solution. Double negative 1 makes positive 1, equals 10. And then subtract 1 from both sides. 3y equals 9. Divide by 3, and y must be 9 divided by 3 is 3. And we get exactly the same solution as we got up here. You see those numbers must be the same. Remember, it doesn't matter how we solve it. How we solve is our preference. The solution, if there is one, should be the same. So for this, clearly we get the same solution, negative 1 comma 3, and we're good with this one. So that is, again, how the elimination method works. If we solve this one by elimination method, I would choose to eliminate x. Okay, so in fact, let's do this one also, that we've already solved this one by elimination method. All right, so I went ahead and copied the system from the point where the fractions were eliminated. So let's solve this now by elimination method. This time, again, because x has a coefficient of 1, that's the easier one to use to make our elimination. Therefore, I'm choosing to eliminate x. Although y would also be easy to eliminate, wouldn't it? Look at the y side of things. I have 2 and 12. So all I would do, if you want to eliminate y, opposite of 12 is negative 12. So you would multiply the top by negative 6, right? In fact, let's do that. Since we solved for x earlier, let's do y on this one. And since we eliminated x in the previous one, let's eliminate y in this one. So distribute negative 6 to the first equation. We get negative 6x. Negative 12y equals 12. The second equation is 5x plus 12y equals negative 78. Add opposites. Those add to 0. Negative 6x and 5x makes negative x. On the right side, we have negative 78 and 12 makes negative 66. See how quickly, by the way, we get to the answer for this one? So sometimes elimination is a preferred method of solving systems. All right. Now, in the computers actually use a elementary row operation using Gauss-Jordan elimination method, which we talk about later on solving systems, which works well with the larger systems. These smaller systems, it really doesn't matter. Some methods are more efficient than others, but my favorite is elimination method of the two, between substitution and elimination in general. Okay, so we got x to be 66. We can back substitute in the first equation. We get 66. plus 2y equals negative 2. Subtract 66 from both sides. We get negative 68 because it combines with negative 2. And then, of course, you divide by negative, but by just 2, we get negative 34 as the solution. Precisely the same as before. 66 comma negative 34, and we have exact same thing down here. All right. Now let's take a look at another example. Okay, we're going to use elimination method for this other example. So the example is 9x negative 5y equals 1, negative 18x plus 10y equals 1. So the ones I've done so far, by the way, the two I did, once with substitution, other with elimination method, these actually had solutions, so nothing out of ordinary happened. So the question might be, well, if a system is dependent or inconsistent, what could happen when I do this? How do I know that I have a dependent system or an inconsistent system? Well, this example should clarify that for us. Let's say I want to get rid of the x. Okay, so our focus is on just the x's. I have negative 18 in the second one, 9 on the first one. So it's easier to multiply, let's say, first equation by, let's say, 2, correct? Multiply by 2 to create the opposite. So I'm going to do negative 2 times the first equation. Now, when we do multiply by negative 2, by the way, it's going to become negative 18x, negative times negative, positive 10y, and negative 2 times 1. Remember, you reach all the way across the equal sign. Don't just stop on the left side. It goes both. You got to multiply the entire equation by that constant. And we're going to keep the second equation unchanged the way it was. Negative 18x plus 10y. Let me... let's see. Actually, I don't want to multiply by negative 2. Just caught my own error, right? I want to multiply by 2 because I was about to cancel and I see they are not opposites. No worries. Then there you go. You erase this one. Now it looks good. Equals. It's because I write, think about life in general, and that doesn't work out sometimes. There you go. Okay, now we have that. So I multiply the first equation by 2. I got 2 by 9, 2 by 5, 2 by 1. Second equation did nothing to it. Now, remember, the intended consequence was this. The unintended consequence is this. And let's see, y just happened. They happened to turn out to be opposites, right? So we add, we have nothing on the left. Instead, we have 2 plus 1, 3 on the right side, right? Now, 0 clearly does not equal to 3, not even on a good day. So, because this is a false statement, true? This is false. So we have a system that is inconsistent. So that would be the sign. The sign the system is inconsistent. You get a false statement, the variables disappear, and you get a false statement. Remember, inconsistent systems have no solution. Ultimately, what is the answer? The answer is not inconsistent, by the way. That just identifies the type of system. What is the answer? This is the answer. The answer is no solution, and the solution set has nothing in it. So we use this Greek letter phi to indicate symbolically, then there is no solution. Some people write it as solution set with nothing in it. Now be careful, don't do this. Okay, there's actually an element now in the set, so be careful, don't write it like that. So any one of these would be good for us. And you just observed an example of a system that was inconsistent, no solution. Now let's take a look at another one. We haven't done a dependent system yet, right? So let me make one up. It's easy to make one because in a dependent system, the equations are not independent. That is why they're called dependent. So I'm going to write the second equation as negative 8x plus 2y negative 18 equals negative 18. And you can pretty much visually see what I just did. I doubled up on everything on the first row, right? Multiplied everything by -2. And once we multiply by -2, we get the second equation. Now, let's say we didn't catch this, and I want to eliminate the y, variable y here. So how would I do that? Multiply the first equation by 2. Multiply, we get 2 times 4 is 8x, and 2 times y is -2y, and 2 times 9 is 18. Okay, so multiply by 2. The second equation is -8x plus 2y, and that is equal to -18. And let's add together now. Once we add, again, the intended consequence was this. The unintended is this one and this one. Notice the left is 0, nothing left, and neither on the right side, nothing's left. This time we have a true statement, right? The statement is true. The one up here was false. We have a true statement. And because we have a true statement but no variable to work with, so this is the sign of a dependent system. That means those two equations, one was a constant multiple of the other. That's a dependent system. Again, that's just to label the system. Remember, dependent systems are also consistent. Therefore, they have infinite solutions. So if there are infinite solutions, can we find a couple of them? Sure. Here's, let's say, x and y. And I'm looking at the first equation because it's easier to remember. They're really the same equation. Let's look at the easier one. Let x be 0. When x is 0, y would be -9. There you go. So the solution set is going to be 0, -9. That's one solution, right? Do we want more solutions? Sure, let's do just one more. I'm going to let y be 0. When y is 0, x is 9/4. That would be another solution. We can find infinitely many solutions. Just pick your own x or your own y, not both your own x and y. So for example, I'm not going to say 3/4 is going to work. I cannot pick both of them. I have freedom over choosing one. The equation will take that freedom away from me for the other one. So here, again, I said I have freedom over choosing y, but I circled x. Again, you can, as long as you choose one, the equation must decide on the other. So there you go. Now, for a dependent system, how do we write the general solution set? This is how you can write it. The solution set is going to be, for example, you make x to be an arbitrary value. This means this is my solution set. See, I have x, means your own x. Pick whatever you want for x. And then you just plug it into here and solve for y, right? So let's solve for y. 4x minus y is 9. So 4x minus 9 would be y. And there you go. You just put 4x minus 9. There you have it. Which really doesn't give you a number, right? It just gives you symbolic, again, representation of a solution. What does this set read again? It says, pick your own x. This would be your y for your selection of x. And that's what exactly we did here. I picked x to be 0. And this says, okay, then in that case, y is -9. So that's the generic way of writing it. Could we have written this the other way around? The other way around would be this. Well, pick your own y, right? We could have done that. Pick your y. This time, let's solve the equation for in here. Let's solve it for x, because we want to know what x should be for a given y. Solve for x, subtract y from both, add y to both sides, divide by 4, and we get 1/4 9 plus y. Or you can write it as 9 plus y over 4. They're the same thing. 1/4 of a number is the number divided by 4. So I'm just going to write it as a fraction. 9 plus y over 4. There you go. Again, what does this mean? Give me a y. Whatever. I'm going to give you, I don't know, something that works out nicely. -1. How's that? So suppose somebody picked -1. Okay, for your pick, 9 minus 1/4 would be 8/4. The answer is 2. So here's a solution to -1. So that's again the significance of how this works, this way of writing the solution set. All right, so we are done with this portion of our work. Let's take a look at now another example here. Let's take a look at another example with this time we're going to look at 3 equations, 3 unknowns. All right, now with 3 equations, 3 unknowns, I have it down here because we have linear systems. Remember, our focus was on linear systems. So this time when we have a linear system, 3 linear equation, that is, with 3 unknowns. If we were to graph these, each equation now in 3 variables, call them x, y, z. Each equation will result in a flat surface. Okay. Now there are a number of configuration, a number of ways these surfaces could come together. So for example, there you go. The 3 surfaces could be the same. Here, the Roman 1, 2, 3 that you see here are surfaces 1, 2, and 3. So the 3 surfaces are the same. This would be like, let's say, in your book, the pages of a book. When you pick up a book, all the pages kind of stack on top of each other. So that's what you have. They have all points in common. This would be an example of a dependent system. Okay, just like we had 2 lines overlapping, dependent system. So this one has infinitely many solutions. Look at this one. The way the surfaces come together, now they come together on a common line. This one also has, that's also a dependent system. It has infinite solutions. Okay. And this one, points of a line in common, that one has infinite solutions. Again, if the difference is how the surfaces come together. The fact that there is a line in common means there any point on the line is a solution, right? So I have a point here, solution, 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 solution. So these have infinite solutions. This one is the ideal situation for us, where you have a single solution. So the 3 surfaces come together at a corner point. Okay, so for example, if I look at a box here, okay, that would be another example of a system that has a common point right here. That would be, let's say, a solution. Why? Because remember, each surface represents 1 solution. So here's surface 1. This one, the bottom, is surface 2, and the front is surface 3. All 3 come together at a common point. All right, so that would be another illustration of a single solution. And of course, these other ones, they have no points in common, so none of these have solutions. These are all inconsistent systems. They could be 3 parallel surfaces now together, or let's say 2 of them are parallel. These 2 are parallel, crossed by a 3rd one. The fact that the 2 are parallel, those 2 surfaces, there will be no common solution to them, right? No commonality, so no solution. And this one, there are pairwise. Those 2 come together, these 2 come together, these 2 come together. So with respect to each other, they kind of have common points. Not kind of, but they do have common points. But with respect to the other one, they don't. All right. So for example, if I look at the 2 surfaces here, numbers 1 and 2 come together. 3 is green. See, 3 is going its own separate way. It doesn't connect to those common points where 1 and 2 are connected. And here we have surface 1 and 2 overlap, they're overlaid and parallel to the 3rd one again. So all the ones on the bottom are inconsistent. None of these have solutions. And the ones on top, all of them are consistent systems. This one, infinite, infinite, infinite number of solutions. And the first one, part A, that one is a single solution. All right. So it's good to know the geometry of this. Again, we don't expect you to draw the surfaces by hand. I don't do it myself by hand anyway, unless I have to. So let's take a look at actually an example now. Knowing the geometry of what could happen, how do we solve a system of 3 equations, 3 unknowns? Now, because we are adding another equation and another variable instead of xy, now we have this third variable z. So you would expect that this problem is going to take longer to solve, right? The more complex the system, the longer it takes to solve. By hand, that is. Usually you do this on a graphing calculator or a calculator that has a computer algebra system, or on a software. Then the point is moot. 3, 4, 5, 10 equation, 10 unknowns. Now they're solved readily thanks to technology. But let's go through this the traditional way, the hard way. All right, so remember, coming to this point, we have substitution elimination method, and we're going to do this. Let's do this elimination method, not substitution method. So when we try to do elimination method, and the first part, by the way, elimination or substitution are done the same way. We need to choose pairs of equations. Now there are 3 equations here, right? There are 3 choose 2 or 3 ways I can pair these equations together. Here's what I mean. I could pair first equation paired with the second one, 2x plus y minus z equal 5. Or I could pair first one equal 2 with the last one, the third one. And the other pairing would be second and third, right? You could do 2x plus y minus z equal 5. And the third one is x minus y plus z equals -2. Those are my only choices. Now, which of these? We don't need all 3 of them, by the way, but we definitely need 2 of them. So which 2 are the best? This example I made up. Notice there's a bunch of 1s or -1s in front of the variable, so it really doesn't matter. But sometimes it does matter if the numbers are not that good. So for this one, generally we picked variables that we can eliminate easily. Okay, so for example, this would be an ideal pairing because next step is to do elimination method. Okay, once we pair them using elimination method, now if I simply add these, notice the z's add to 0, y's add to 0. Usually this doesn't happen. It's just this one I made up. It's an easy one for illustration, and there you go. See, x is solved. So that's how we pick the pairs. That was just showing you how do we pair them. How do you know which pairs? That would be the ideal situation. Now, because I don't want that to happen, I'm going to pick these 2 together, and I'm going to pick, doesn't matter how I do this. No, you'll see why. And I'm going to pair these 2 together. Now, let's say I want to eliminate, now you have a choice. Do you want to get rid of x, y, or z? Well, clearly z, they're opposite in the first one, right? Not opposite here. So I could choose to eliminate z. But then for this one, also, the y's are opposite. So I could choose y to eliminate. But let's say I want to choose z to eliminate. So I'm going to forego this one. Don't worry about that one. In the first system, just add them together. I get 3x plus 2y equals 7. You see that? Now, in this system, the second one, remember the first one, I eliminated z. In this one, I must eliminate z. Okay, it's not like, oh, the y's are easier, so let's eliminate y. Well, I have to eliminate z, the same variable. Because if I don't, look what happens. If I just add these 2 equations together, if I just add them together, I get 2x plus 2z equals 0. See, now I have an equation here and a different equation. One of them, first one, has xy, the second one has xz, so I cannot solve them yet. So that's for that reason we eliminate the exact same variable. So let's eliminate z here. How would I eliminate them? I need opposites. I'm going to multiply the bottom one by negative. Okay, that would give me a negative z, and that should eliminate it. So the first equation is x plus y plus z equal to 2. The bottom is negative x plus y minus z equals 2. Let's add them together now. The intended consequence. See, that's what we wanted. This is the unintended consequence. Unfortunately, they eliminated. I wish it hadn't, but it does. Because the reason I say I wish it hadn't, suppose it hadn't, I get something like 3x plus 2y equal 4. Something like that. At this point, in general, not with this one, you would have two equations, two unknowns, and the unknowns will be exactly the same because we eliminated the same variable from each system. Okay, but for this one, again, the unintended consequence happens. And so we have 2y equals 4. And from this, we get y is 2. Now, once we have the solution for y, we can back substitute in this one. The equation is 3x plus 2 times y equal 7. That gives me 3x is equal to, subtract 4, we get 3, so x is 1. There. We got that one. We solve for x and y. It's easy to solve for z. You have a whole system to go back to. Any one of those. Remember, this is a system. That means the solution must work in every one of them. Not just one, not just two, but all three of them. So I'm just going to plug in for x in here and for y in the same equation, the third equation. So the third equation is x minus y plus z equals negative 2. And z is, move 1 to the other side, we get z is negative 1. See how easily we can solve it? Of course, that was an easy system too. Okay, now what does the solution look like? In the case of two equations, two unknowns, the solution was an ordered pair. In case of three equations, three unknowns, the solution, if there is one, is going to be in the form of an ordered triple. X, Y, Z. This is how they typically look like. So for this specific example that I've done, it's going to be, make sure you put parentheses. Don't do 1, 2, negative 1 like that. That's incorrect. So we just want to put in, it's incorrect because it's not in parentheses. That would imply that we have an ordered set of numbers. The ordered triple. X followed by y, followed by z. And there you go. We keep them alphabetical. So if you have P, Q, P, Q, R, then you keep it in that order. If you have A, B, C, keep it in that order. X, Y, Z, that order. And there you have it. The solution to the 3x3 system. Let's do one last one here. I'm going to do an example of a system that has three variables, but only two equations. Now, in order, by the way, to be able to solve any system, no matter how large, as long as it's a finite number of equations, for any system, we have to have at least as many independent equations, independent is the keyword there, as many independent equations as there are variables. So the example I just made up here, this example, I have how many equations? Two equations. How many variables? X, Y, Z. Three variables. The variables are greater than equations, right? So for this one, I will not be able to give you a specific 1, 2, 3 solution. The answer is going to be very general. Okay. Now, what if you have more equations than variables? Then that's fine. Let's say I have x plus y equals 7, 2x minus y equals 10, x minus 3y equals 15, 2x plus 3y equal, I don't know, 11. You see that? A couple of these are redundant, right? Because I really only need 2 of them. Why do I need 4? And assuming these are all independent as well. So I don't need more than 2 equations. So if I have more equations than variables, then chances are these equations are redundant. Okay, 2 of them are redundant. And when we say that these 2, which I don't know which ones, the 2 are a linear combination of another ones. Okay, so anyway, the fact that I have more variables than equations here, I have 3 variables, 2 equations, I cannot find a unique solution. So how are we going to work this one? At this point, what we do is we're going to report the solution. We call it a parametric form, in parametric form. And here's how it works. So for example, I'm going to solve for y in the second equation. That's going to be z minus 13, right? Add z to both sides. And there you go. So that's going to be the solution for y. Okay, notice I don't have a number. But then I'll show you how to get a number out of this. We will actually find a solution for this. So there's your y in terms of z. Now, then we need to solve for x. 3x is equal to, move 5y to the other side, 4z to the other side minus 7. Okay, and divide by 3. So x is going to be, let's see, x is going to be what? Divide by 3. So I'm just going to go 1/3. How's that? 5y plus 4z minus 7. Now we know what y is, right? We can substitute for y in here and combine like terms. Or one thing I could have done, this isn't wrong, by the way. You can finish this one. We can probably, that would be easier. Let's plug in for y in the first equation. That way I just get x in terms of z and we'll be almost done. So that's 3x and negative 5y. Y is z minus 13. Negative 4z equals negative 7. That would be 3x and negative 5z plus 65. Negative 4z equals negative 7. Combine like term, 3x negative 9z, subtract 65, negative 72, right? And finally, not almost finally, move z to the other side. I get 9z minus 72, and then divide both sides by 3. Okay, so x becomes 3z minus 72 divided by 3 is what, 24? And there you have it. So we have the solution for x and y in terms of z, notice. So one way, there are actually 3 ways we can write the solution set. One way is this. The solution set is choice of x, 3z minus 24, the order triple, comma, y, z minus 13, comma, and z is itself. You see that? I don't solve for z. Z is itself. And there is a solution set. Notice I don't have an answer for specific answer because I don't have enough equations. So there's the solution. Now, if I want a particular solution, let z be 0. When z is 0, then now I can plug in for z here, here, and here and get a specific solution, a very unique solution. When z is 0, the solution is going to be 3 times 0 minus 24, negative 24. 0 minus 13 is negative 13, and z0. Here you go. This is one such solution. If you want, let z be, what number do you like? Whatever. Probably saying 1, 2, 3, 4, 5, or negative 1, negative 2, whatever. You can let z be pi, by the way. All right, let's go fancy. You're going to let z be pi. Remember pi, 3.14 approximation. All right, pi. So my solution set is 3z. That would be 3 pi minus 24. Z minus 13. That would be pi minus 13. And z is pi. There you go. So anything you like, you can let it be. And the other way, by the way, notice I solved for y in terms of z. You can solve for z in terms of y and get a solution in terms of y. Okay, now let me do that. I'm going to pause the video, do that just so the video doesn't take to be too long, and I'll show you we get exact same solutions in just a moment. Okay, to show you again another parametrization of the solution. So what I did is this. I actually now solved for z in the second equation, this one, in terms of y. Solve for z. Remember it was y minus z equal 13. So solve for z. Move z to the other side, bring 13 to the left side. I get y minus 13. There you go. Now z is in terms of y. Okay, and let me see. Move z to the other side. Yeah, so it's going to be that. And then we can substitute for z in the first equation. Okay, now, oh, actually, it was y minus equal negative 13. Good thing I caught that. Negative 13, so it's going to be y plus 13. Good. Now we're going to substitute in the first equation. The first equation was 3x negative 5y, okay, minus 4z equals negative 7. First equation in the system. Combine like terms, distribute and combine. Negative 4y and 5y to the left of it makes negative 9y. And then 4 times 13 is negative 52 equals negative 7. And solve, we get 3x is equal to 9y plus 45. Divide by 3 and x is 3y plus 15. Okay, so the solution now is going to be in terms of x, y, z, but in terms of y. So x is 3y plus 15. Y is whatever y is, and z is y plus 13. You see that we get what we call different parametrization of the solution set. And remember we had a solution here. Negative 24, negative 13, 0. Let's see if we can generate that solution. Let me write the solution that I had. And 0. Let's see if we can come up with that solution again. This is when y is negative 13, right? So I'm going to let y be negative 13. Let's see what x and z end up being. Negative 13 plus 13 is 0. So z will be 0. Put negative 13 here. 3 times negative 13 plus 15. That's negative 39 and 15, negative 24. So x would be negative 24. You see how we got the exact same solution and like we did before. It's just different parametrization, they call it. All right. Probably spend too much time on this one, but I think it was well worth it. All right, so we're done with that. We are done with this section. Hopefully the lecture is going to help you now do the exercises that you're going to do on your own. All right, and as always, thank you for watching.